Today I'm going to tell you about all the stuff that I've been doing on cosmic fireworks from merging stars. And in classic astronomers fashion, just before I started this, preparing for this talk, I was like, I want to make a talk where I compare stars to humans. And so I started Googling stars like us. I didn't find any good astronomy related stuff, but I found possibly what has been like the most amazing thing that I've ever found on the internet, which is the Us Weekly magazine back in the 2000s had these really corny photographs of celebrities doing normal stuff and tried to convince people that, oh, stars are actually just like you. And so I found Christina Aguilera shopping for groceries and saying, I really love baked potatoes. I found Chris Hemsworth saying, staying hydrated, as you can see. And my favorite one, Jessica Alba eating Mexican food. And the caption to that actually says, when in Rome, Jessica Alba tries traditional cuisine for dinner with her family. So again, it's kind of not clear whether she was actually having Mexican food or not, but that's what they say. But regardless, stars, they actually do share some characteristics with human beings, after all. The first is stars have a life cycle, just like human beings. Stars are born, they grow old, and then they finally die in spectacular fashions. The environments in which stars are born shape them. I grew up in India, so I have a very high tolerance for spice. Similarly, stars that were born in our own galaxy are substantially different than stars that were born in other galaxies. We are all made of stardust. Most of you are probably familiar with this. We are literally made of the same material as stars. Everything that we see around, the screen, this table, all of us, was synthesized in the cores of some stars at some point in our lives. But what's really important for the next 10 or 15 minutes is stars, just like human beings, don't like to be by themselves. They like to make friends. And a lot of stars have a lot of friends. Our sun has planets. This is a plot. This is not to scale, as any of the plots that Aurora showed. This is very much a vibe-based plot. So our sun has planets. There are other suns, have some stars have other stars around them. Sometimes those stars can actually be similar to each other. Sometimes the stars may look different from each other. And there are some stars which, sometimes the stars can actually have more than one star orbiting them. There can be 3 stars that are orbiting each other. There can be 4, 5, 6. They can have all sorts of fantastic combinations out there. What really amazes me is how common it is for stars to have companion stars. So I know we are all very used to looking up at the sky and seeing one sun. But if you look at the stars that are similar to the sun across the Milky Way, the chance that a star like the sun will have a companion star is actually 50%. So we are really, we are very used to looking up and seeing one star, but seeing one sun, but we were just a coin flip away from having 2 suns, or having more suns than, more than 2 suns. And then if you start looking at stars that are more massive than the sun, by the time you reach stars that are 10 times the mass of the sun, you're almost guaranteed to have a companion star. So it's very, very common for these stars to have all of these friends. And just like the friends that we make really shape who we are and decide what we will become when we grow up, similarly, the presence of a companion to a star actually shapes the evolution of a star. It has significant impacts in the different stages that the star goes through its life. An important step in this evolution happens when the star, one of the 2 stars, typically the more massive star, runs out of hydrogen gas in its core. This is similar to what's going to happen to our sun 4 billion years from now, but the exact same thing happens. Let me see if I can play this. Yeah. So when this more massive star runs out of hydrogen gas in its core, it's going to expand, right? And it's going to become a giant star that is hundreds or 1,000 times the larger in radius than its initial self. And when this expansion happens, if there is anything in the way, it's just going to gobble it up. So over here, it's plotted, we see the Earth, but the same thing is true even if you have another star that is present over there. So as the star is evolving and becoming 1,000 times larger, it just gobbles everything up as it becomes a giant or a supergiant star. And so that's where our story begins. So this is what a typical giant or a supergiant star looks like. It's got this really hot, dense, yellow-colored core inside in the center. And then it's got this gigantic atmosphere or an envelope that extends to thousands of 1,000 times. So just for some scale, for a typical giant or a supergiant star, the dense core might be similar to the radius of the sun. And then the entire envelope might actually be the distance between the Earth and the sun. So it's a really, really elongated star. And now if the star has a companion, unfortunately, our little companion star finds itself embedded inside this envelope of the star. And this companion is not actually just sitting there, right? It's going around the star. And so the same, it experienced a lot of friction from all of the gas that is just around it. It's very similar to what happens when you have the International Space Station or any satellite that's orbiting the Earth. When it dips below into the atmosphere of the Earth, it starts experiencing friction forces that causes it to lose altitude very, very rapidly, and eventually it just crashes into the Earth and there's a explosion. Similar thing happens as the star is orbiting around. It just goes inside, and speeds up until eventually it crashes into the core, and just there's a big, big explosion that releases tons and tons of energy and causes the brightness of the star to increase by factors of thousands or 10,000 times. Here's an example of this in action. So this is a star in our own galaxy. This plot shows the brightness of the star on the y-axis versus years in the x-axis. So initially in this phase, which is marked by 1 over here, from 2002 to 2004, or even to actually 2007, this star was kind of just doing its own thing. It was just being a star. But in the background, what we could see is that this was not just one single star. It was actually 2 stars, and they were going around each other with a period of about 1.5 days. So it was just rotating really, really quickly. But during this time, what it was also doing was slowly coming closer and closer and closer to each other. Until one day, finally, at the start of 2008, it just decided to the stars decided to collide into each other and then brighten by a factor of 10,000. And then you can see that this is this plot shows a GIF of a before and after image. So the before image is when the star was just doing its own thing. And then the after is when it just brightened substantially. And there was this huge, massive explosion that lasted for almost 2 years. And then it slowly faded away as the energy got dissipated outside. And so this is what I mean when I say there are cosmic fireworks that you can get when 2 stars just crash into each other in this violent explosion. What's also exciting is when such explosions happen in our own galaxy, they go off and we see them as a spectacular light bulb. But they also serve as a light bulb in the sense that they light up the gas and dust around them. So our Milky Way has a lot of these really dusty clouds. And they really, when you look up at the sky when the Milky Way is above, it looks really fantastic. But they're also very difficult to study because these dark patches are full of very dense gas and molecules that make it difficult for us to look through them. And it really makes it difficult to understand what exactly is going on there. But every time there's an explosion that happens, it sets off a light bulb. And so it basically illuminates all of the gas around it. And it provides a way of studying this really fantastic gas over here. And so now what I'm going to show is a video of the Hubble Space Telescope that was pointed at this stellar merger explosion that I just showed you. And what you will see is the explosion went off, and it lights up all of the material around it. This is all real data. This is not an artist's impression. This is not a simulation. This is right in the center is the big light bulb, the stellar merger that happened. And as you can see, as time passes, as the light travels further and further out into space, it reaches more and more larger distances and illuminates dust clouds and dust sheets and gas that is further and further away. And so this really provides you a way to study the gas that would otherwise be invisible. And I think this is one of my favorite videos in astronomy. Just the fact that you can just point a telescope at this and you see this without any simulations, without any requirement for any artistry. This is truly, truly fantastic. Is it still going? Yeah. Okay. What's also cool is that this was in our own Milky Way, in our own galaxy that's really nearby. But we can now discover these stellar merger explosions in other galaxies that are millions and millions of light years away from us. How do we do that? We do that using robotic telescopes that are taking pictures of the sky every night. So in the background over here is the telescope that Caltech operates called the Zwicky Transient Facility, ZTF. What telescopes like this do is basically they operate completely automated manner, and what they're able to do because of this is just take pictures of the entire sky, the full sky that's visible to it every single night, day after day after day. And what that allows you to do is I can take an image that was taken today, I can compare it with an image that was taken yesterday and try to see what changed between them. Are there new stars that came through? Is there something that changed in brightness? So here's an image. There's a new image on the left, an old image on the right. Can anyone spot what is different between the two images? This dot right here. Yep, exactly. So there is a new source that appeared in this image. There's a nice big galaxy out there. You can see the spiral arms of the galaxy. So this is an explosion that took place in this galaxy that was powered by a stellar merger that happened in this galaxy that was, I think, 20 or 30 million light years away from us. And that's pretty cool. Unfortunately, the data doesn't come with the yellow circles, so we have to figure out ways in which we can detect these things in an automated manner. So we have algorithms that can take this new image and subtract it from the old image while accounting for a lot of different factors that would have changed at the time of the new image and the old image, and identify all of these new explosions that just pop up in these images. And then we can, what we do is we basically identify all of these explosions, and then we study them in more detail and try to figure out what was the powering mechanism behind these explosions. So with the Zwicky Transient Facility, the telescope that I told you, we have discovered about a dozen or so stellar mergers that have happened in galaxies at distances ranging from 10 to 50 million light years from us. They happen in all of these, the crosses mark the positions where all of these transients, where all of these stellar merger explosions happened. And you can see that there's a really wide range of spectacular galaxies that are producing all of these stellar mergers. And once we identified all of these stellar mergers, we were able to learn a lot of details about what was the evolution of, what kind of stars are powering all of these stellar mergers, what are the different mechanisms that are responsible for bringing these stars so close to each other, and how basically stars that are in double or triple or multiple systems evolve so that we can see these mergers. But what really stuck out to me was how common these are. And what we found out was that most stars in the universe can actually merge with their companions. The number that we came up was greater than 70% stars in the universe can actually merge with their companions. So this is really, really something that is extremely common. And I did most of my PhD in the era of social distancing and isolation, and this kind of was very, very heartwarming in the sense that at least there's no social distancing out there, right? There is one problem in this really nice picture, though. All the stellar mergers that I showed you, they were all in other galaxies, right? They're all in these really, really far away galaxies. But the very first picture I showed you was of a stellar merger that happened in our own galaxy, in the Milky Way. So why did we not find any stellar mergers in the Milky Way when we did this very, very systematic search? I think we think that this happens because the same reason. All of these really dark patches that we see over here on this picture, they're basically these really dense molecules and gas that we like to call cosmic dust. And there's a lot of dust in our galaxy that we need to see through in order to detect all of these stellar mergers or these explosions happening in our own galaxy. But this dust is really pesky because it absorbs all the light that's happening, that absorbs light from everything that's happening behind it. So it's kind of a wall in front of us that we cannot see through this wall. Fortunately, dust absorbs most of the visible light that you and I can see, but it's relatively transparent to infrared light. So here is a very classic image of the Boots void. This was a patch on the sky that really puzzled people in the late 20th century, where there just seemed to be like a void in the sky, right? Like, why are the stars everywhere around, but there's just suddenly this one patch of sky where there are no stars. It turned out that there's a lot of fascinating explanations that people proposed, but the simplest explanation turned out to be very true, is that there's just a lot of high density of cosmic dust over there. And so it's absorbing all the visible light, but if you look in infrared light, then you can actually see all of the stars and there is no problem. And so in order to find these stellar merger eruptions or explosions in our own galaxy, we need to look at infrared telescopes rather than look at telescopes that are sensitive to just visible light. And so that's what we decided to build. We decided to build this new telescope called WINTER. It stands for the Wide Field Infrared Transient Explorer. So wide field is a telescope that has a wide field of view. Infrared is at infrared wavelengths. Transient means all of these it's meant to detect these eruptions that are that appear in the sky and then go away over a few months or a few years. And an explorer is just explorers, because we are all explorers. One of my favorite things of working on a project that is titled Winter is I get to show this slide. And as of a year ago, this has changed to Winter is here now. And hopefully our telescope has a better ending than Game of Thrones. But here is our team in front of the Winter telescope, all happy faces. This telescope is installed at Palomar Observatory in Southern California. This is an observatory that all the Caltech telescopes are located at. It's a really magical place. It's been really fun. I really love the observatory, so I would recommend anybody, if you are ever in San Diego, it's like a 1-hour drive from San Diego. 100% would recommend. I'm here somewhere in this picture. But with winter, so we have been trying really hard to find one of these stellar mergers in our own galaxy. We came close. We found a stellar merger in Andromeda galaxy, which is one of the galaxies that is the closest galaxy to the Milky Way, other than some smaller ones. And we found one in the Andromeda galaxy. It was a really dusty merger that was found because of winter's infrared sensitivity. So over here, you can see the new winter image, an old image, and then the difference image. So over here, because Andromeda is so close by, we can see the star in the old image as well and in the new image. And then when you subtract it, there is still some residual at the location of the star. So that shows that the star brightened up. So whereas we get more light from the star in the new image compared to the old image. And we think that this brightening happened because the star engulfed its companion and it merged with its companion. But we still haven't found anything in our own galaxy, and we are really looking hard. And maybe one of the reasons why we haven't found it is because winter is not very sensitive. Like maybe we need more sensitive telescopes to find these stellar mergers in our own galaxy and also in some other galaxies. Fortunately, fortunately, as of 2 days ago, next year, the Nancy Grace Roman Space Telescope was supposed to be launched, and that is going to be the most sensitive infrared telescope ever. That has been the most sensitive infrared search telescope, I must say, that has been launched. And it is going to be really amazing at finding all of these really hidden stellar merger explosions and other kinds of explosions that we just haven't found so far because we don't have the right tools. And so once the Nancy Grace Roman Space Telescope launches, we are going to be able to see stuff like this. So we are going to be able to make maps like this, where we see a star, then it becomes a merger, then it illuminates the dust, and then we are going to be able to trace how it illuminates the space around it for years and decades since then. So it's really going to be an extremely exciting time. Fingers crossed that it still gets launched. Yeah, so here's some takeaways from my talk. Some things that I think you should remember. I showed a bunch of stuff, but the few most important things are most stars in our universe have companion stars that merge with each other. It is really very common thing that stars do in the universe. These merge and explosions look cool. I hope I've convinced you from those videos that they're actually really spectacular objects. And they also teach us a lot about how stars go through their lives and what are the different changes that happen to a star as it goes through its life. The Roman Space Telescope is going to be really spectacular, and it's going to revolutionize our understanding of finding these mergers in our own galaxy, in other galaxies, and for a whole wide range of science that is beyond mergers. It's really going to be an extremely powerful mission. Finally, stars are indeed just like us. And if you're ever bored, please go and check out all of those Us Weekly magazine pictures. I really enjoyed them. And thank you for listening.